All right, here we go. 6.1, displaying bivariate data. So what do we mean by displaying bivariate? Well, we are looking for patterns on the x and y axes. So instead of just having one set of numbers, we have data that is associated with two sets of numbers, and so that's why we begin using two different axes. You might remember this from algebra class, where we took numbers and we plotted them. For example, this number here looks like it is about 15, and then it's associated with the number 47. And so this is data that's been collected, and our x-axis is known as the explanatory, and our y variable we're going to call the response variable. So, in summary, we now have two values that are associated with each data point, and then the variables are the explanatory variable, and this one we put on the x-axis, and we refer to it kind of as the independent variable. And then the y variable is the one that responds to it. So we call it the response variable because it is affected by the x-axis, by the x variable, the explanatory variable. So here's an example, example A. Which variable is explanatory and which is the response? Time spent studying, score on a quiz. Which one affects the other? Hopefully you said to yourself, the time spent studying is the explanatory, and the response is the score on the quiz. That is, our quiz does not affect our time spent studying, rather it's the reverse. So here we've got an example, paper recycling and glass recycling in different countries. We saw this earlier in chapter 5. So which variable affects the other? Does the glass affect the paper or the paper affect the glass? It's very tough to say in this case, and so we would be able to put one on either axis. It wouldn't really matter which one we did. In this case, I would suspect that paper was recycled more often than glass, and so if one of them is going to affect the other, it's probably the paper affecting the glass. So we put the paper on the bottom and glass on the top, and then we take all those data points and we plot them. Yes? Notice here on the axes, we don't start at 0. It doesn't help us to start at 0. It is somewhat convenient. Sometimes you'll even have values that are negative, so we'll have to float an axis above. In this case, that 0 should have been probably down here on the bottom, but whatever. Okay? There is flexibility in doing that, in creating your graphs. We are no longer going to use socks as our summary statement. Instead, we're going to use scoffed. The S stands for strength. So the first thing we're going to look at when we plot this data is how strong is the data in relationship to the two variables. We can see here that this first one is very strong. Those data points are tight together. They almost form a line. Here, not so much. Here, we can hardly tell if there is any pattern at all. So we call that a very weak, if no, strength. This is kind of what we talk about in the whole chapter, by the way. This is the correlation coefficient. We're going to get a number that will be tying to that. The C. C is the same from last time. It is the context. We need to summarize our graphs and descriptions in context. Yes? Make sure that you always use words that relate to that. We don't want the numbers just sitting by themselves. O, still the same, outliers. We're going to treat them a little bit differently. We're not going to do the same math, but they tell us whether or not we have strange values that don't fit the pattern. Almost forgot what the STR word was there. Now, some of these outliers skew our results more often than others. So here again is a graph showing our outliers, and here's an outlier. And in this case, this outlier has more effect than that. And you might ask why. And notice this graph is graphed using this region, and this dot is outside that region. Whereas this graph is within the region that we are graphing, and so it is not as influential. This is a dot that we would toss out. We wouldn't even use in our calculations. Okay? F. F stands for form. What is the shape of the pattern? And there are three different types of shape. There are linear, and then there is nonlinear, and then there is no form. So linear, as you might expect from your days of algebra, looks like a line. Nonlinear can look like a different shape from algebra. You might remember this looks like a parabola. And then obviously no form means there's dots all over the place. We cannot tell what's going on. Okay? So form stands for those three. D, direction. Which way does the pattern head or go? So here you can see there's basically two directions we can have. We can have a negative direction, we can have a positive direction, or obviously no direction. Okay? And again, we can see here a strong negative, a weak positive. All right, so here's an example. Here we have car weight and gas mileage. And we can see here that this is a somewhat strong, I wouldn't say it's really strong, but the variables, the explanatory variable is the weight of the car. The response variable is the gas mileage. There are no outliers in this problem. That is, in terms of the weight of the car as it affects the gas mileage. We can see that it is somewhat strong in that it has a negative direction. Okay? Whereas if we look at height and IQ score, we can see that the explanatory variable is the IQ score, but the response variable does not seem related at all. That is, height is not affected by one's IQ score. Thank goodness. Otherwise, some of us would be in trouble. So there is no form. It's very weak. Yeah. Okay. And outliers are everywhere, you could say. All right, well, that's the lesson. Good luck in the homework. Again, we're working with bivariate data, data that has two numbers associated with it. And we plot them on the x and y axis.